Hello guys, welcome back. So here we have another question on communication systems from GATE 2023. The signal to noise ratio SNR of an ADC with full scale sinusoidal input is given to be 61.96 dB. The resolution of the ADC is dash bits rounded off to the nearest integer. So here they are asking about ADC. So what is ADC? Analog to digital converter. And here what is the signal? Full scale sinusoidal input. So our input signal is sinusoid. So it is something like this. And now you want to discretize your amplitude, right? That is what is digital. So what you will do, instead of having continuous amplitude levels, you're going to limit it to some finite amplitude levels, right? So it will be something like this, right? And this number of steps, right, will depend on how much bit we take for encoding each of these levels. For example, if there are 8 levels, each level will encode it as 0000001 up to 111. So if this is a and minus a, I can assign this to level of minus a and this to level of a, something like that. So this number of steps, usually since it is given in bits, we have 2 power n. For n bit, we will have 2 power n levels. So what will be the step size delta here? So delta will be the total divided by the number of steps. So total is a minus of minus a divided by the number of steps, 2 power n. So this is 2a divided by 2 power n, which is nothing but a by 2 power n minus 1. So this is our delta. So this is what is called as an ADC. So now if you say they are asking the signal to noise ratio. So signal to noise ratio, the SNR is nothing but signal power to noise power. So here what noise they are referring to is the quantization noise. Because from here to here, when you are approximating it by a single level, you are making an error, right? So there is an error here. So this error is considered as a quantization noise in case of an ADC. And this noise we say has a distribution of, it has a uniform distribution from minus delta by 2 to delta by 2. Why? Because at max it can make only an error of minus delta by 2, right? Because once you're above that region, it goes off to the next bit. It increments or decrements, right? So this is the distribution. And since it is a uniform distribution, for the probability density integral to be equal to 1, its amplitude should be 1 by delta, okay? So this is the quantization noise probability distribution function. So now we need to calculate signal power and noise power. So signal power for a sinusoid is nothing but amplitude square by 2, right? In this you're integrating any sinusoidal function. So power is sine square. So sine square, let's say t with dt over 1 time period. So this will give you whatever amplitude square, a square by 2. So in this case, let's say the amplitude is a. So it is going to be a square by 2. So next we need to calculate the noise power. So noise here is having a probability distribution function. It is not deterministic, right? So noise power is nothing but your variance of your distribution. So variance of this distribution is nothing but, if you remember, we calculated from our previous videos, right? So this is gonna be delta square by 12. And what is delta square? Delta is a by 2 power n minus 1. So it is a square by 12 into 2 power 2n minus 2. So we have both our signal power and noise power here. So the SNR is a square by 2 divided by a square by 12 into 2 power 2n minus 2. So a square goes away. So 2, 6. So it is 6 into 2 power 2n minus 2. So if you observe, SNR depends only on the number of bits on n, right? And SNR usually is expressed in log form. So, and since it is power, we need to take 10 log of 6 into 2 power 2n minus 2. So this is nothing but 10 log 6 plus 2n minus 2 into 10 log 2. So this, if you write it out, this is 10 log 6 plus 2n log 2 minus 20 log 2. So 10 log 6 minus 20 log 2 is 1.761, and plus 2 log 2 is, again this is not 2 log 2, it is 2n into 10 log 2, so it is 20 n log 2. So 20 log 2 is 6.02 into n. So depending on n, your SNR will vary, and in this question they have given SNR as 61.96. So this is equal to 61.96, and they have asked us to find the resolution of ADC in bits is dash. So they are asking us to find n. So this, if we try to calculate, find n, it comes as 9.999, so which we can round it off to 10. So the number of bits to achieve this particular SNR is 10 bits.